So as I've discussed, we got to deal with chemistry in this class, and so this molecular interaction has to do with the chemistry portion. And as I said with physiology, you want to learn these concepts. These concepts we're learning at the beginning, you want to get a strong hold in them, so you don't have to keep learning them over and over. I know chemistry gives some of you guys a little bit of anxiety. I try to keep it as simple as possible, just using the chemistry that we're not gonna be have to equal equations, balance equations, and so forth. I just want you to have a working knowledge of the chemistry so you can apply it to what's happening in our physiological systems. Okay, so I try to keep it chemistry for dummies. Some of your chemistry professors might beat me up on the way I explain it because I try to keep it more simplistic so you can understand the concepts and use those concepts in the physiology. All right, so we got to do it, but chapter 2 will be a little bit of a long one. I try to spend more time on this because I want to make sure you guys understand the concepts, and people also, you know, we're not all from a chemistry background. Some of you do, some of you don't. So those that do, this will probably be just piece of cake. Those that don't, it might be a little bit of struggle, but we will get through it. And if you're still having trouble with it, come see me during the office hours or so forth. All right. When we looked at that level of organization in the first lecture, the bottom level, the most simplest level, was that of the atoms. Okay, so this is what we are made of. All mass is made up of various forms of these atoms. And these atoms can bind together, and we'll talk about that bonding in a little bit here to make molecules. So atoms individually, they'll bond together to form that next level of organization, molecules. But let's first look up what makes an atom an atom. All right, you can see here is atom. It's made up, it has a nucleus, kind of like your cell has a nucleus in the middle. In the atom, there is this central nucleus, and it's made up of P, which are protons. Protons in that they have P, positive charge, and neutrons. These have no charge, they're neutral charge. Okay, so essentially the nucleus has a positive charge to it because it has positive and neutral. So it has a positive charge to it. Around the outside, in what we call shells, you'll see them as rings, almost like, but this is a simplified version, is you think of this as three-dimensional, almost like a ball. These electrons are floating around, and these clouds are shells around these protons. See, these electrons are much smaller, but they have a negative charge. Electrons are negative charge. And so what you can see for an atom, basic atom, is how many protons do we have in here? We have 4. How many electrons do we have out here? 4. So in your atoms you find on your periodic table here, if you have 4 or whatever number of protons, you have an equal amount of electrons on the outside. Okay, so essentially these atoms have a neutral charge to them. Okay. The mass number. Okay, the mass number is the amount of protons plus the amount of neutrons. Okay, what we're worried so much about is the atomic number, the number of protons. So in this, how many protons do we have? We have 4. The atomic number of 4, 1, 2, where are we at? We're at beryllium. Okay. So that is that for atoms, right? If this number on the periodic table, hydrogen, what's it have? It has 1 proton. Helium has 2 protons, has an atomic number of 2. Okay, and remember, how many protons there's an equal in these atoms, there's an equal amount of electrons. So if you have a helium has 2 protons, it's also going to have 2 electrons. Okay. So now we kind of have to delve into this periodic table and what this is showing us. If you read across the periodic table, you see it goes 1, 2, then back to the left, 3, 4, 5, 6. Once we reach here, we come back 11, 12. Okay, but keep in mind these numbers, 11, sodium also has 11 protons, but also has an 11 electrons. Okay, because we got to talk about these electrons and where they exist around in these atoms. So let's look at how these atoms relate in the periodic table. I know this might cause some anxiety, but I just want to try to keep this as simple as possible and explain it in a layman's term to kind of give you an idea of what because this is going to help us determine on bonds and ions and so forth. Okay, but looking at the periodic table, you can see each horizontal column here is called a period. Okay, you can see the first period here, the one in period 1, only contains 2 atoms. The second contains 8, third also 8. And what this is telling you, you can see the atomic number 1, 2. This is telling you the atomic number will tell you what? It'll tell you how many protons, but it'll also tell you how many electrons. And the electrons are going to give these atoms kind of their reactivity with other atoms. Some of them want to form bonds, some of them do not, because of the arrangements of the electrons, the number of electrons that they have. Okay, in each of these periods going across, okay, they can contain multiple orbitals. Okay, you can see here s orbitals. And how many electrons does it look like the s orbital? 1s contains 1s, 1s, 2 electrons. Again, 2s, 2 electrons. How about the p orbital? What do you see? 6 electrons. P block or p orbital contains 6 electrons. Okay, and the d contain 10. Okay, the good news is that we're going to play more up in here, or let's look at it through here, because this is where our chemistry, these are the more common atoms we will be finding in our in our body, our systems. Okay, we do have to deal with some of these magnesium and so forth a little bit further down, but for the most part, we're going to be playing up here. Hopefully, you guys have all heard of carbon life form or a carbon life form. There's that carbon sitting right here. Okay, but let's look at each period. Period 1, we got hydrogen and helium, right? What we see, what I said is the S can hold 2 electrons and then it's filled. Okay, if we have like the third one, what happens? 2 electrons are filled in the 1s, and then lithium would have 1 electron in the 2s. You can think of them almost layers of these shells, these orbitals. Okay, they're the clouds that surround, these clouds here that surround, that move around these nucleuses of the atoms. Okay. 2s, if we look at beryllium, okay, now we got the 1s and the 2s shell filled. Now to completely fill a p orbital, we have to have 6 electrons, okay, to fill this 2p orbital. So 2p's here, look at here. Okay, and the key is that atoms are stable when their electron, when these orbitals, these shells, are filled. So less stable over here. This is going to be, these elements or these atoms here are going to be very stable because what do they have? They have their P shell fill. Okay, these are elements like helium. Helium's a little bit different because what does it have? It has just the one S, but when we get down to neon, argon, carbon, what do we have? We have the shells completely filled. These are called the noble gases because they're not very reactive. If you're very stable, you're not going to be reactive. All right? What gives the reactivity is these other elements. You can think of the noble gases as the cool kids. Everybody wants to be like the cool kids, or most people want to be like the cool kids and be in the popular group or so forth, but this is what everybody strives to be. Or if you're an artist, you want to be an artist. You know, if you're a basketball player, this is a professional basketball player. Okay? So however you want to look at it, whatever you strive, what's perfection to you, these are what you would be looking at. This is them. All right? These other elements are looking at, oh, these guys are nice and stable and perfect. Okay, we want to be over here. So let's look at how some of these atoms, these different atoms, can get here. All right, let's first look at, let's say, oxygen. All right, how could oxygen be like neon electron-wise? Okay, what does oxygen have? Oxygen, okay, has the 1s filled, the 2s filled, but looking here, it only has 4 electrons in this p orbital that can contain 6. So how can oxygen get to be like neon electron-wise? Yeah, it needs to gain 2 electrons. Okay, and we're going to see that these atoms can form bonds and either borrow or steal electrons, depending on the atoms, to get basically a stable configuration like these noble gases here. Okay, so how many electrons, if you were to share electrons, how many electrons does oxygen need to share? It needs to share 2 electrons with another atom to be electron-wise like neon here. Okay, let's go to the opposite end of the spectrum. So the easiest way for oxygen, well, let me reiterate, the easiest way for oxygen to get to here is to gain 2 electrons. Okay, otherwise to get to be like helium, it would have to lose these 4 and lose these 2, and then it would be like helium. It's easier for it to gain. The elements over here, close to the noble gases here, want electrons. Okay, they want to take electrons. They want to take them or they want to share them. So they want to be, they're reactive. They want to get like these here. You can see these elements here, chloride, fluoride, they are very, very reactive. What do they need? It's kind of like if you needed $50 to get the toy you want. You're like, oh man, that's a steep hill to climb. I gotta get $50. How am I gonna do that? Whereas if you only need $1, oh man, how can I get this dollar? You're jonesing to get it. That's chloride. Chloride wants I just need 1 electron. Give it to me, give it to me, give it to me. So these elements here want to be very reactive. They want to get an electron. Okay. How about on this side of the periodic table? Okay. Let's look at, we're going to see sodium quite a bit. Okay. What's the easiest way for sodium to be like one of these noble gases? Gain 1, 2, 3, 4, 5, 6, 7 electrons to look like argon? Or is it easier, hey, I'll just give off my electron, and electron-wise, now I'll be like neon. Yeah, so these elements, or sorry, these atoms on this side will give away. Okay. Over here, give, give, give. Here, take this electron, all right, and give it away. I can be like what I view as my perfection. Pro basketball player, okay, famous artist, whatever you're aspire to be, this is those noble gases. Okay. The wanting electrons, give me electron, give me, give me, give me, is termed basically electronegative. So as we move across this way, across this direction, so towards the neon glasses, these elements are more electronegative. Where these elements over here are very little electronegativity. Okay, I don't want, just take it. Okay, so that is what's going to cause the reactivity, what's going to allow these atoms, because remember, atoms bond together to form molecules. And you can see some of these atoms, oxygen is very prevalent in the war because it wants to be very reactive. It wants to gain electron, wants to form bonds so it can be more like neon. Okay. Let's look at some special cases here. Not special cases, but some interesting ones in that carbon. Carbon is interesting in that how many electrons to get to be like neon? It needs 1, 2, 3, 4. Okay. If you form a bond, you're sharing an electron. That means you're gaining 1. Carbon wants to gain 4. So you can see carbon can form 4 bonds. It can share electrons with 4 other atoms if it wants to. Okay. Therefore, we can make all these very complex molecules. What if I have a carbon, a carbon, carbon? Now I got all these other atoms I can bring them to these outside carbons. I can form these very diverse molecules because carbon wants to form 4 bonds. I can't have as many diverse with oxygen because how many does oxygen? Oxygen just wants to make bond 2. It just wants to share 2 electrons. So really it only wants to do bond with 2 different things. Think of the most common. What do we have? Water, right? H2O. Oxygen with 2 water molecules. It's formed its 2 bonds. All right? It's not going to gain 4 more hydrogen. Okay? So that's what makes carbon somewhat unique, and also it makes us carbon life form. It's very diverse in that we can make these complex molecules by using carbon as the central atom. Okay. One other unique one, and one that we'll be talking about a lot, is hydrogen. Hydrogen, remember these over here are low in electronegativity. Low electronegativity want to give away. So hydrogen doesn't try to gain to be like helium. It will lose its electron. Okay, it will give away its electron. Hydrogen, how many protons do we have? 1 and 1 electron. What happens if hydrogen gives away its electron? What's it consist of now? Basically a proton. There's no neutron in the normal hydrogen form here. So basically, you'll hear me use when hydrogen's giving away its electron, becoming what we call an ion, we'll talk about in a sec. Hydrogen ion is just a proton. So you'll hear me use hydrogen ion or proton. I typically use proton, and proton means that's the ion of the hydrogen atom. Okay, but we'll talk about ions here in a bit. I hope you understand. But all right, so give, give, give. Molecules over here, take, take, take. So this is going to be our basis on how reactive these molecules and how many bonds they will form to create these molecules, right? Because we're going up in level. We got atoms as the most simplest. Atoms bond together to form molecules. So as we said, electrons. So the outer shell is called the valence electrons. So outer shell, what do we have? We have 6 valence, but we need 8 to get if we're oxygen, we need 8 to get to the most stable. Okay, we need a full outer shell to get stable. Okay, incomplete shells, outer shells, makes molecules more reactive, and as we move up, we get more electronegative. These elements or these atoms want electrons. These ones are, hey, just take my electrons. Okay, electronegativity means they want. Gimme, gimme, gimme. Okay. I used to use the term that the analogy that these elements, my daughter's fluoride, because she's like, give me. And my son, all right, would be more like lithium. Hey, you can have it. You can have it. Although my son's starting to move in this direction, starting to become more electronegative. Okay, electronegative, want. Less electronegativity over here. And take the electron. Okay. So let's look at some of the bonds we can form. Okay. The ones we'll be dealing with, the biological molecules we're talking about, are going to form what we call covalent bonds. Covalent bonds are bonds in which the elements share. Okay, they share electrons. Okay, atoms share. We'll see in ionic, there's a taking of electrons where in covalent, each atom's playing nicely, they're sharing the electrons. Okay, you can see here, oxygen. What is oxygen? Oxygen wants 2 electrons. So how many electrons does it need to share with another molecule? It needs to share, or with 2 molecules, it needs to share 2 electrons. Here we got 2 atoms of oxygen, and each one is sharing electron to fill the outer shells of each oxygen molecule. Okay, this is a covalent bond since they are sharing the electrons. Okay, we'll talk about nonpolar and polar. In this instance, this oxygen, they have the same electronegativity. They both want it the same amount. Therefore, these electrons will be shared equally. You're just as likely to find an electron in this shell as you are to find it in this oxygen shell. Okay? There's no pull of electrons to give us a negative pull or a positive pull. The charge of those electrons is shared equally. There's no pull, positive or negative pull, that creates a non-polar molecule. Okay, How about our friend water? Water is the lifeblood, is everything. But let's look at oxygen. Gimme, gimme, gimme. Electrons, hydrogen, you can take it. What do you see happening with electrons here? Are the electrons equally between hydrogen and oxygen when they form this bond? No, the electrons are held closer to oxygen. Remember oxygen, what does it have? What's its number? Okay. 2, 4, 8. It has 8 protons and 8 electrons. Now it's pulling in 2 more electrons, so it has a negative charge to the side because it's not going to share equally with the hydrogen. The electron is pulled closer to the oxygen than the hydrogen, and so the hydrogen, which had a proton and an electron, but this electron's being pulled closer to the oxygen, now there's just this proton almost by itself, but sharing with oxygen, it has a positive pull. So this forms what we call a polar molecule. Okay, the charge isn't equal across the molecule. More negative over here because oxygen's hoarding the electrons with the bond with hydrogen. And there is a positive pull on this end. Okay, well, that's the difference between nonpolar and a polar molecule. Okay, sharing equal distribution of the electron charge. You get a nonpolar. Okay, unequal distribution of the electron, you get a polar molecule. Okay. What we see also with water, what do we see? We see oxygen binding to one hydrogen, oxygen binding to another hydrogen. This is a single bond because we're just sharing one electron here and one electron there. A double bond is we're sharing 2 electrons between these 2 atoms, and this would be a double bond. You would actually see this written, you saw it written out, oxygen, O, and you might see it with 2 lines. That's saying double bond. You can see here with water, there's just 1 line. That's a single bond. So when you see this nomenclature, the 2 lines between atoms, a double bond. Let's look at nitrogen up here. Nitrogen gas is N2. Okay, the subscript here tells me, hey, we have nitrogen and there's 2 molecules of nitrogen. Okay. We see water. What do we got? H2O. There's 2 molecules of water and 2 atoms of hydrogen and 1 atom of oxygen. So N2, how many electrons does nitrogen want? 1, 2, 3, and then electron-wise, it's like neon. Okay, so what do you think? How many, when in this atom of nitrogen, how many electrons do you think they share between each other? They each want 3, right? So they're going to share 3 electrons to create what we call a triple bond. Okay, so you see this notation. If you see these lines, 1 line means single, 2 lines a double bond. That means they're sharing 2 electrons, and 3 lines sharing 3 electrons. Okay. So going back to our friend, carbon, right? What makes it unique in that combine 4 groups to it? You can form 4 bonds. So this makes it so you can make these very diverse molecules. What if I have carbon here? If I have a carbon over here, this carbon can still, even though it's bonded to this carbon, it can still form 3 more bonds. So we can get these very complex, large molecules by using carbon as one of the core atoms in our molecule. Okay, that's what makes carbon somewhat unique, in that it's the ability to form so many bonds, 4 bonds. Okay. So as you can see, I have this in 2, and this should be gone here. Have this in 2 places, polar, non-polar, because we're going to be using this terminology. So I want to make sure you guys get this terminology down and the kind of the concepts between it or behind it. Okay. When we say non-polar, the electrons are evenly distributed across the molecule. So there is no negative side of the molecule and a positive side. A classic example of a nonpolar molecule is a fatty acid. Okay, it has this long chain of carbon. Even though carbon is more electronegative than hydrogen, because we have this long chain, we get an even distribution of the electrons, and therefore it's considered a non-polar molecule. Okay. Polar, we've already seen the most notorious polar in water, right? Because oxygen's hoarding the electrons, where hydrogen's like, yeah, take it. Okay, and therefore there's a negative pole on the oxygen side and a positive pole here on the hydrogen side. There's no equal distribution of the electrons. Oxygen is holding them closer, and therefore it creates a pull and gives us a polar molecule. And what we're going to see is polar likes polar and nonpolar likes nonpolar. These two don't like to mix together very nicely. It's kind of the old adage, if you take water, a cup of water, and put oil into it, does the oil just go nice and diffuse across the water? No, the oil stays next to the water, to the oil. They stay in a clump because they're non-polar. They don't want to be mixing with the polar water molecules. They're sticking together. These non-polar fatty acids are sticking together because polar and non-polar don't mix nicely. So another term you will see for molecules is hydrophobic and hydrophilic. Hydro, water. Phobic, water fearing. Hydrophilic, water loving. Remember what kind of molecule. So this isn't polar or non-polar, but think about what kind of molecule water is. It's polar molecule. So typically hydrophilic. Okay, molecules that are soluble in water are hydrophilic. They love water. So typically polar molecules, because polar likes polar, we'll see ions. Also, like it in water, they will dissolve in water. So anything with oxygen, nitrogen, phosphorus, these are electronegative molecules. So typically they're going to form molecules that are polar. Not always, but typically ones that contain lots of this will have polar molecules. And therefore, water's polar, these would be hydrophilic. They're very easily soluble in water. Whereas nonpolar molecules, like lipids, these are long carbon chains, are typically hydrophobic because they are not soluble in water. Nonpolar stuff does not like to be soluble in water. More nonpolar is either less likely to be soluble in water, and therefore that would characterize a hydrophobic molecule. Okay, so this terminology you will be hearing quite readily. There are hydrophilic hormones and hydrophobic hormones. Hydrophilic hormones can dissolve in the blood. Blood is made up a lot of water, and therefore those hormones can dissolve in there. The hydrophobic ones, we'll see, like steroids, will have to have a carrier to help because they don't like to dissolve in the water. Okay, so we'll see this terminology throughout the semester, but hydrophobic, typically nonpolar molecules that don't like water. Hydrophilic, typically polar molecules that love water. All right, so that's with our covalent molecules. We got our covalent bonds, make us polar or nonpolar molecules. There's another bond, okay? And let's start ranking them in strength-wise. Covalent are the strongest bonds. They don't like to be broken very easily. It usually takes more to break covalent bonds. Okay? Where ionic bonds are lower in strength. We're going to see there are some bonds that are even lower, but it's covalent, strongest. Underneath it is ionic bonds. And what's taking place in an ionic bond? Remember, those molecules forming covalent bonds were sharing electrons. Okay, some of them not as nicely as other. Oxygen's pulling it more towards itself, where hydrogen's just letting it go. Let's look at when we have these highly electronegative. Chloride. Gimme, 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 gimme. I want. It's very highly electronegative because it only needs one electron. Where sodium, if it loses one, it's like neon here. So it's like, yeah, take it. Okay, they don't even need to share. This one's willing to give it up very easily, and this one wants. And therefore, chloride actually pulls an electron. Okay, it is transferred. That electron is transferred over to the chloride atom. Now the chloride is negative and the sodium is positive in charge, and basically it's almost like an attraction. Okay, they're not sharing an electron, but they have this strong attraction because one is positive and one is negative. Right? Positive and negative attract. You guys have done magnets before. Positive side to the negative side of the magnet, and you get an attraction. Okay? It's a fairly strong bond, but it's not strong like covalent bonds. So what do you need to do? With these, if you put them in water, the bond actually breaks. You put salt. This is salt. Sodium chloride is salt. You put it in water, what happens to it? It doesn't stay as salt. It breaks off into sodium and a chloride. Okay? If this breaks, you have sodium now as an ion, and what does it have? It has a positive charge. And chloride, since it's taken an electron, chlorine molecule will have a negative. And this creates what we call ions. Okay, and ionic bond, molecules that make up an ionic bond that break. All right, you put them in water, they do what we call ionize, split apart. The positive ion, the sodium one, is called a cation. Chloride, which is negative ion, is an anion. Okay, on the next slide we'll look how this forms, how these bonds are broken when we put this sodium chloride into water. Because remember, water is polar. There's a negative pole and a positive pole. Which side is positive? The hydrogen side. This molecule is negative. So you're going to see the positive pole of water is going to surround this ion. Whereas with sodium, it's positive. Where's the negative pole of water? Oxygen side. So water is going to surround it, but in this turn, the oxygen will be oriented towards sodium. Okay. So that's what we see here. Okay. We get what's called these hydration spheres. These hydration spheres, the pole of the water separates and ionizes that sodium chloride into a cation and an anion.
All right, so strength-wise, there is a third. So covalent strongest, ionic second in line, and the third in line is what we call a hydrogen bond. So not actually sharing of electrons or passing of electrons here. This is more of attraction between polar molecules. Remember, polar molecules have a negative pole and a positive pole. Such thing as like water. Water's a polar molecule. Or here we have a positive pole to the water and a negative pole. So what do we see? We see the negative pole is attracted to positive pole of another water molecule. And whenever you see these dotted lines, okay, or these little slashes or little dots here, book, that shows you a hydrogen bond. That's a classic way of writing the hydrogen bond. Okay, again, it's an attraction between those two poles. There's no electrons being shared. There's no electrons being transferred. Okay, it's just this attraction here. So you can see this is definitely a weaker bond. There's no electron sharing and so forth. All right, but even though these are third in line strength-wise, many of your molecules, such as DNA, remember DNA has two strands. The DNA strands are held together by hydrogen bonds. But in one DNA, there could be millions of hydrogen bonds, and therefore, even though it's a weak bond, with so many of them, DNA is a very stable molecule. You've seen those cold cases where they've gone back and looked at the DNA 50 years later. All right, there's the strength to these bonds. In water, when you put water, if you drop water gently on a surface, does the water dissipate out? No, the water usually stays as a droplet because the hydrogen bond is creating this surface tension that keeps the water together. So it's holding it together with these hydrogen bonds. So lastly, in the weakest of bonds or forces of attraction are the van der Waal forces. And this is basically a attraction between the electrons of one atom and the nucleus of one atom. You can almost see there's a temporary bipole between the atoms and created where the nucleus is on one side and electrons on the other. Same here, and you get this force. It's the force of attraction because it is more negative here in this atom and more positive here in this atom. Okay, so again, this is weak, so this is easy to pull apart, unlike a covalent bond where it takes a significant amount of energy to pull the covalent bond together. Van der Waal forces are fairly weak, be disrupted fairly easily. Okay, this also allows molecules to pack, kind of looking down here. Saturated fats that are very straight. Okay, these atoms here, this is a carbon-hydrogen chain, create a van der Waal force. Okay, and allows these molecules to pack tightly together. Right. So that's the last of the bonds. So let's do our order. We got covalent bonds, very strong. That's the sharing electrons. We get a transfer electrons in the ionic bonds, and then we get that nice strong force. They are second in line. And then hydrogen strength-wise, and then hydrogen bonds. Right, that's the attraction between the two poles of two polar molecules, such as in water. And then lastly, the van der Waal forces, this attraction between the nucleus and the electrons of one atom. And so another terminology, we'll see, we get our bonds together to make these molecules, and we can make what's called inorganic or organic compounds. Inorganics are usually less complex, usually lack oxygen or carbon, but there are like carbon dioxide here. We'll see carbonic acid and bicarbonate. They do have carbon, but these are simple, less complex. Can be ionic or covalent. Okay. The more complex molecules, organic compounds, are what we call biomolecules, which we'll be talking about in a bit here, contain carbon. Remember, carbon can make 4 bonds, so we can make these very complex molecules. We can make these very large, complex molecules because what can we do with carbon? We can make 4 bonds with each of our carbon atoms. All right, they are always covalent, so not ionic, like you've seen with the organic. And kind of the 4 major biological molecules, and we're going to be walking through the different characteristics of these, are our proteins, our carbohydrates, our nucleic acids, and our lipids. So we'll be looking at each of these class of molecules and looking at the differences of them and looking at the different components or different types of these molecules. Okay, but these are organic or biomolecules. We make very large, complex, covalently bonded molecules. So now that we've described these bonds and the way we put these molecules together, let's see how these molecules exist in the body. Our body is roughly 60% water. Some cells more, some tissues have more water, like your brain's almost 70% water. Your bones are even watery though, even though they're so dense, they're about 30% water. So these molecules that we were talking about don't usually exist solely as a solid. They exist in these solutions. They're dissolved in water. All right. And so what is a solution? A solution is we have a solvent, dissolves the substance, and the substance being the solute, or in our case, most of our solution are solutes. There are multiple things dissolved in our solutions of our body. Okay. But our solvent, what is our solvent? Is water. So we have these solutions. We already described we had the ECF, right? The blood and the interstitial fluid. Those are solutions. Okay. They are watery with many different solutes dissolved in them. And even inside the cell is a solution. It has a watery environment with many things dissolved in it. And one terminology we have to use is, we do have to do some chemistry, but I try to keep away from the numbers. I don't want to do the mathematics. What I want you to understand is what this term molarity means. Okay, molarity is telling you concentration, how concentrated a solution is. And concentration means how much solutes are dissolved in the solution. Okay, so that is what molarity is essentially telling you. You'll see a term 1 mole. 1 mole is 6.022 times 10 to the 23rd power. So many molecules. So if you have oxygen, if you have 1 mole of oxygen, in that 1 mole of oxygen, you will have this amount a number of molecules, oxygen molecules. Or let's say salt, NaCl. Okay, you put salt in water. Okay. You put this many molecules of NaCl in water, that is 1 mole. Okay, and if you put that many molecules of salt in 1 liter of solution, that is a 1 molar solution. Okay. What if you took double the number? You doubled this number and put double the amount of molecules of NaCl in. Now we're keeping it in just 1 liter solution. We're not doubling the solvent, the water, or the solution. We're only doubling how much salt in. How many molar solution will we have? Yeah, we would have 2 moles in 1 liter solution divided by 1, and we would have a 2 molar solution. Okay, so that solution, that 2 molar solution, is much more concentrated than the 1 molar solution. It's got double the amount of solutes, so it is much more concentrated. That is a concept you guys got to understand. So what I simply, if you have 2 molar solution or 1 molar solution, you realize that this 2 molar solution has double the amount of solutes. It's much more concentrated. It's very as simple as that. We're just going to be comparing these solutions molarity wise, and we're going to add a term later called osmolarity, but we'll discuss that in later on. But what I need you to do is just be able to recognize the difference in concentrations, because we're going to be using what's called a concentration gradient, and you need to realize there's a difference. There is one side's more concentrated than the other, or let's say it's more concentrated outside the cell compared to inside the cell, the solutions. Okay, so you got to recognize this when we start talking molarity of a solution. Okay, I'm not going to make you calculate molarity on an exam. What I need you to do is understand the concept of what molarity is telling you. It's telling you how much solutes in one solution compared to the other. So you guys can't really discuss in groups unless you have groups together, but which solution is the most concentrated? We got 1 molar, 0.5 molar, 500 millimolar, and 300 millimolar. Here you kind of need to make a distinction, because we're talking, again, we are using the metric system. This and this are actually the same concentration, because there are 0.5 molar. Millimolar is much smaller, and so it by the thousands, so you have to move this decimal point 3 places. So this millimolar actually equals, there are 500 millimolars in half a molar solution. Okay, where we're going to be dealing mostly in our classes, we'll be using millimolar and what's also called osmolarity. So we probably won't be comparing this to this. We'll be comparing some millimolar solution to another millimolar solution or milliosmol solution. Okay, but you got to make these distinctions, because we're going to be using this terminology molarity to look at differences in concentrations between solutions, especially looking at concentration of solution outside the cell compared to a concentration of solution inside the cell. Alright, so keep this in mind. If you're having trouble with this, please come see me in office hours. I will be happy to make sure that this distinction is clear, because we will be using this throughout the semester. Alright, so let's move into our real chemistry and how the cells operate. basically our cells are operating through chemistry. And what is chemistry? We're making chemical reactions take place. Okay. In chemical reactions, we have reactants or substrates. Okay. Moving to products. So here we have CH4. Okay. CH4 is it's not telling you how it's bonded, but it's telling you what atoms are involved. We got the big like carbon atom, and it's bound to 4 hydrogen. Okay, covalently bonded. Now we have 2 oxygen molecules. Oxygen, 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 oxygen. Okay, these are covalently bonded. We saw this earlier. What would this polarity of this molecule be, this oxygen molecule? Just to give you a quiz. Yeah, it's oxygen, oxygen. They're going to equally share those electrons, so this is a non-polar molecule. Okay, but let's look what's happening in a chemical reaction. Look on this side, we got 1 carbon, 4 hydrogens, and we got basically 2 times 2, so we have 4 oxygen atoms. What do we end up with? This is the reactants. Here's the products. We end up with CO2. Here's our carbon bound to 2 oxygen. That's our carbon dioxide. And we form 2 water. We got oxygen, the big red, with 2 hydrogen. But let's count our numbers. Let's count our atoms. 1 carbon on this side. How many carbons on this side? 1. 4 hydrogen. How many hydrogens on this side? 1, 2, 3, 4. 4 oxygen. How many on this side? 1, 2, 3, 4. So what's taking place in these chemical reactions? Okay, we're not changing atoms, we're not losing, we're not gaining different atoms. All we are doing is basically changing the bonds. Okay, where hydrogen was bonded to carbon before, now hydrogen is bonded to our oxygen. So that is essentially what's taking place in these chemical reactions, is we're changing bonds. We're not changing atoms, we're not losing or gaining these atoms. All we're doing is changing the configuration on how these atoms are bonded together. That is simply what's taking place in these chemical reactions. And you'll see the nomenclature. You'll see boom, boom, drawn with a arrow sign. This would be our reactants. We start with many reactants, and then how much reactants actually take place and turn to the product here. Okay, but again, I want to stress all we are doing is changing in these chemical reactions, or changing the bonds between the different atoms. We're not losing or gaining any atoms here. In our chemical reactions. Okay, some reactions will only go essentially in one direction. Okay, when we start talking energetic of the reactions, you'll see why. But some chemical reactions only go from, say, reactants here to the products. But many reactions go in opposite direction. This product can turn to this, and this can go in opposite direction and change and turn that way. What we look at is what's the rate? What's the rate of reaction going one direction, and what's the rate of the reaction going another direction? Okay, we will see that there is, in these reactions, there is a point in which the rates are equal. It's going in one direction, the same rate as it's going in the other direction. So we're not changing the amounts on either side. Okay, we're going to get in this to a little bit more when we start getting into the energetics of reactions. But just realize some of these reactions are going in both directions. Okay, but what, again, in these reactions, what's taking place? All we are doing is changing the bonds. Okay, there's a lot here, I'm not going to count it, but what you can see is the hydrogens on this side is the same amount of hydrogens you would find on this side. Oxygen on this side, same amount of oxygen you would find on this side. All we are doing is changing the bonds that are taking place, okay, or the configuration of the bonds. Okay, let's describe this law of mass action. We talked about on the previous slide, reactions can go in this direction and reactions can go in that direction. Okay, for these different reactions we're going to look at. All right, if you kept the same amount of concentrations, same amount of products, same amount of reactants, at a certain point, the rate at which it goes in this direction will be the same as it goes in this direction, in this top portion here. You have P and L, individual molecules, bind together to make PL over here. The opposite can take place. PL can separate from each other and become individual PL molecules. So we got going in this direction, in this direction. If everything is left the same, the amount of PL in the solution and the amount of P and L in the solution remain the same, at a certain point, the rate at which it's going in one direction is the rate same as this. We get this, what we call reaction equilibrium. Okay, so this is going, changing to PL the same way as PL is converting back to PL. They are the same. So we're not getting changes in the amount of either of these because they are going at the same rate. The law of mass action is saying what happens if we added. So we're here, we're at equilibrium, but now we're going to add more P. Let's say we just added P. No L, just P, but we added more. Now, like the teeter-totter, what's that make that side? It makes it heavier because we just added a bunch of P. This will change this equilibrium because the equation wants to equal out. How can we do that? Is if we convert more P with the L into P and L. So how do we do that? Look at the rate of reaction. The rate of reaction converting P and L to PL is bigger or faster rate than it goes in the opposite direction. So this will convert more of this to this than this to that. And eventually what will happen? Equations will equal out again. Okay, and that's the law of mass action. Okay, if we add to one side, basically the rate of reaction is going to change to bring us back to the equilibrium in the reaction. What's the opposite of this? Let's say we added, instead of adding P here, adding P, we added PL. Okay, now this side would be heavy. If we had this side, let me get my little marker here, we're going this direction, where this side's heavy, what would we have to do? This rate of reaction going in this direction would have to be greater than the one going in that direction, and would help bring the teeter-totter back. Okay. Let's look at, because we'll be doing this kind of in the opposite direction, in add P. What if we took away P? What if we made this even less? We took away, say we took away some this here, and we're left with just this amount here. Okay, this would make this side lighter if we took it away, and what would our teeter-totter would be that way. So how can we convert that back? We make this rate of reaction bigger, so now we equal out again. Okay, so that's law of mass action. We add, we gotta, on this side we gotta, make the rate of reaction faster. If we took away from this side, we would need to bring the equation back in this direction to get our equilibrium. Okay, I'll try to find some resources on this, because this is one of those that people get a little confused on, and it's important because when we start talking about our buffers, we start talking about our carbonic acid and our bicarbonate system, this is how it operates through this law of mass action. Okay, so definitely want to get this concept down, because we will be using it throughout the semester. Okay, you're going to be able to conceptually recognize what's going on, or else you're going to have to keep learning it over and over through the semester. So definitely get this concept down, because we will be using it throughout the semester. All right. Enzymes, catalyst, speed of reaction. All right. Many of our equations, or sorry, not our equations, our reactions. Okay, here is a maltose. This is basically our, you guys probably heard glucose. Glucose is our sugar. Okay, one of our carbohydrates. And this is two glucose molecules bound together. Okay, your digestive system cannot absorb maltose. Okay, it has to be broken down into individual two glucose molecules. Glucose can be absorbed in the digestive tract, maltose cannot. So what you see though is if you have maltose and water, okay, this equation, you could put maltose and water and maltose is going to stay together. 300 years later, you can come back and most of the maltose is going to still be as maltose. It's not going to convert to glucose. So how can we make this take place? There are enzymes. And we're going to spend a lot of time talking about enzymes. They are proteins that help catalyze or speed up these reactions. And we'll talk about how they do this when we start talking enzymes. And they allow maltose to be broken down into glucose. They speed up the reaction. So instead of maltose staying maltose, if you put maltase in, you'll get much of the maltose broken down into glucose. Okay, so that's the function of these enzymes. They speed up the rate of the reaction. Okay, they speed this rate up to allow it to take place. And we're going to spend a good amount of time on enzymes. I'm just kind of introducing the concept to you in the case of chemical reactions here. All right, these chemical reactions will be sped up by these enzymes here. Okay. So another chemical property we got to recognize is these terms acid-base, and also pH. In our first lecture, we talked about homeostasis and some of the variables that we keep homeostatic. One of those variables is the pH in our body. So let's describe how we get and what the measure of pH is. If you took water, distilled water should be taken out, all this stuff, solutes dissolved in water are removed, and so you should solely have water. If you were to look at it chemically, you would find that water is not just purely water, that a small portion, 10 to the negative 7 molar, right? So that's 0.00000. Okay, what do we got? 6? 1 amount of water molecules are actually ionized to hydrogen ion and what we call a hydroxide ion. Okay, so most of it is water, but a small amount is ionized into these here. Let's look. What is an acid and what is a base? An acid is a molecule that can release protons. So if I was taking acid and put it in water, there would be a lot more of these hydrogen ions in that solution than compared to that 10 to the negative 7, that small amount of hydrogen ions that ionized from just water alone. Okay, so acids increase the amount of protons or hydrogen ions. Okay, again, I'm going to be using that proton. If I say proton or hydrogen ion, I'm talking the same thing. Okay, a proton is basically the same as a hydrogen ion. Okay, but acids increase the amount of these hydrogen ions in a solution. A base, on the other hand, can combine with this. It would remove hydrogen ions from a solution. Okay, so if I took something like sodium hydroxide, put it into water, what you would find is there would be less free hydrogen ions, because this OH that I increase, remember that law of mass action? If I increase the amount of this, so here's my equation. Water goes to proton plus hydroxide. Okay. If I add an acid, I'm going to increase this. Some will go to here, but I've increased so much of this that the amount of the free protons would be increased. But if I add this without adding any protons, this will cause the rate of reaction to be greater in this direction, and therefore this hydroxide ion that I brought in will sop up these, and that would bring down the amount of free protons. Okay, you say, why is this important? Okay, because it's going to determine what number of free protons are available, and this is going to be our measurement of pH. Okay, let's look at the difference between what we call a weak and a strong acid or base. Let's look at this here, hydrogen chloride. If you remember, chloride is on that far right column. If it's chloride's bound to hydrogen, this is ionically bonded. What happens when we put ionic compounds into water? They dissociate, they ionize. So if I put hydrochloric acid in a solution, what am I going to essentially get? I'm going to get all of it is going to turn to ions. So all of the hydrochloric acid I put in, all those molecules of HCl are going to convert and add a lot of these to the solution. Remember, if a molecule can release a proton, it's an acid. In this case, hydrochloric acid releases this, and because it all dissociates, it would be considered a strong acid. Okay, whereas carbonic acid, which we will be dealing with a lot throughout the semester, okay, converts to but if I put carbonic acid into water, this is a covalently bonded molecule. Are covalent bonds easy to break apart and dissociate? No, they're harder. So when I put carbonic acid, only a small amount of this acid actually ionizes into this. Okay, so I will only add a small amount of protons to the solution if I put carbonic acid. If I put the same amount of hydrochloric acid and the same amount of carbonic acid, which solution is going to have more of these free protons? It's going to be the hydrochloric, because all of this dissociates and creates, all the molecules create free protons, where only a small amount with carbonic acid. So hydrochloric acid is a strong acid, it donates all of the protons, where this carbonic acid would be considered a weak acid. The same with hydroxide. Sodium hydroxide up here. Okay. This hydroxide ion, okay, this is an ionically bonded molecule. Same with potassium hydroxide. These are ionically bonded. So if you put these in solution, all of these go to, say, sodium ion and hydroxide. So now, if I put this in, all of those molecules are converting to hydroxide. So I'm going to add a lot of this to it. This would make it a strong base, because remember, these hydroxides are going to bind up these protons. So that is a strong base. For ammonium hydroxide, which is covalently bonded, okay, there's an NH4 and OH. But if I put this in solution, only a certain amount will convert to, will dissociate into the ions, right? And therefore it makes it a weak base. Okay, so the amount that it donates, in this case sodium hydroxide, if I put the same amount of sodium hydroxide at molecules as I put in another solution, I put the same amount of ammonium hydroxide molecules in another solution, which one is going to have more free hydroxide ions? Yeah, the sodium hydroxide, because all of these are going to be converted to OH, where only a small amount in ammonium hydroxide are going to be converted to hydroxide ions. Remember, hydroxide ions make it a base. In this case, only a small amount, so weak. In this case, a large amount, and therefore a strong base. Okay, why do we care about this? Because these characteristics are going to determine our pH of our solution. So what is pH? Let's take a look. pH is basically pH is the measure of how many hydroxide ions I have in a solution. If I put a acid into my water, I take hydrochloric acid and put it in my water, what's going to happen to my amount of this? It's going to go up very largely. The amount of this is going to increase if I have put hydrochloric acid into water. What if I put carbonic acid in solution? Same amount as I put in, same amount of hydrochloric acid. I took another solution and put the same amount of carbonic acid as I did hydrochloric acid. What's going to happen to my amounts of free protons? It's an acid, so it's going to increase the amount of hydrogen ions, but not to a much lesser extent than I would with hydrochloric acid. Okay, the equation, and I'm not going to make you calculate this in an exam, but what I want you to do is recognize what a pH is. What is the equation? Because if you look, an acid is going to make this number greater. Where is this number? This number is this concentration. And so that's another, whenever you see brackets, that's telling you concentration. What is the concentration? I can have brackets, and I'm going to have, let's say, bicarbonate. Bracket would be, what is the concentration of bicarbonate? That's what the brackets mean here. So what is the concentration of free protons? If I put in hydrochloric acid, this number is going to be much larger. If I put in carbonic acid, it's going to be larger, but not extremely larger. But what I want you to recognize for this pH equation is that this number is in the denominator. If I divide 1 by a large number, I'm going to get a much smaller number. If I divide 1 by a smaller number, right, it's not going to be as low a number. So what do you think acids do to pH? Okay, because this is pH is equal to the log of 1 divided by the amount of, so acids increase, make this number larger, and therefore you can see acids make the pH number decrease. Okay. On the opposite end is if I put hydroxide. A base. A base is going to combine with free protons in the solution, and it's going to decrease this number. So now I'm dividing by a smaller number. What happens if I do that? It will go increase in value. All right, so acids decrease the pH, where bases increase the pH. Okay, this is very important because this number, this variable, this pH variable, is tightly regulated in our body. Anybody know where we sit? Okay, here's water. Water's neutral at 7. Okay. Anything below 7 would be considered acidic. Say 6.7, very slightly acidic on the pH scale. 2 would be highly acidic. On the opposite end, let's say 7.4 would be slightly basic because we're above 7, and say pH of 11 would be highly basic. Okay, where I put this number here because this is where roughly blood pH is. Okay, and we keep blood pH homeostatic as 7.4. We have a range roughly 7.35 to 7.45. Okay, you start getting above this number or below this number, and your body might start having problems. When you get too far, you start having organ failure. Okay, so this is a tightly regulated variable, this pH in the blood. So where do you see blood pH? On the pH scale. pH scale means 7 is neutral. Where is blood? Is blood acidic or basic? The homeostatic value for blood. Yeah, it is slightly basic. 7.4 is where is kind of the set point. But again, it's homeostatic, so it stays within a dynamic range. So as I said, our blood pH is tightly regulated. Okay, it is very important. You can see we said normal pH, basically set point is around 7.4. Again, 7.4 on the pH scale, 7 is neutral. So where does our blood? Our blood lies a little bit alkaline. Okay, when we start using these alkalosis and acidosis, alkalosis has to be more alkaline than 7.4. Okay, 7.35, anything below, start going into acidosis. And you can see we don't have to move too far away on our pH scale when we start getting into some serious issues. Okay, so this, you'll see through the semester, this blood pH, we have multiple ways of keeping this within that homeostatic range. Okay, one of our first ways of keeping this in a homeostatic range is called a buffer system. Okay, a buffer system, and the one we're going to be discussing in great detail through the semester is bicarbonate, carbonic acid buffer system. Okay, I'll just write these down real quick. And what is bicarbonate? Bicarbonate is HCO3. Carbonate is an ion. Carbonic acid. Okay, this is a weak acid, and bicarbonate is basically the weak base of carbonic acid, because if I added a proton here, if I added this to this, what would I get? I would get carbonic acid. Okay, so bicarbonate would bind these, remove them, where carbonic acid, if I added it, would increase this amount. So basically a buffer is a weak acid and its conjugate weak base. Conjugate weak base in this case is the bicarbonate. Okay, let's see how this operates. Okay. There's our bicarbonate. Bicarbonate's here. There's our proton, and there's carbonic acid. Remember our little teeter-totter. Our teeter-totter, our law of mass actions. This equation can go in both directions. If I add or subtract one of these molecules, that throws off the equilibrium. That's that teeter-totter. So let's do our teeter-totter. How does a buffer operate to regulate what we're trying to do is keep this, the number of this in the blood, we're trying to keep it within a homeostatic range. We don't want this, the amount of hydrogen ions to go up extremely, get more acidic, and we don't want the hydrogen ions to drop significantly. So we want to keep those hydrogen ions. And so what we have is we have a lot of this, a lot of bicarbonate in solution, and a decent amount of carbonic acid in the solution. Because if we have large amounts of this, change in this will drive my equation either this way or that way. So let's look at more cases. Our bodies create more acids. So like when we're exercising, we create lactic acid, or exercising strenuously, we create lactic acid. What's an acid? It's going to donate protons. So this amount would go up when I'm working out extremely. And what do you think? Say our equation was in equilibrium. My teeter-totter was like this. Now I start working out and I increase the amount of this. What's my teeter-totter going to look like? It's going to be heavy on this side of the equation. Now, because I have lots of bicarbonate and lots of this, the change in this number is what's going to drive which way my equation goes. Because remember, law of mass action, I'm at equilibrium. Now I added a bunch of hydrogen ions. Now how do I get it back? My equation has to be, because this side got heavy, my equation is drawn in this direction, taking my bicarbonate, binding it to the protons, and creating carbonic acid. Because in this, there are no free protons, no free hydrogen ions when I bind it into carbonic acid. And so my teeter-totter's like this. If I draw my equation in that direction, I bring it back. And so by driving the equation in this direction, I'm essentially removing those protons, or those hydrogen ions that we're creating during exercise. Okay. Let's say I start vomiting a lot. Vomiting a lot will take my stomach's acid, and I'm removing acid. Or let's make a more simpler case. Let's say I take a lot of antacids. I take some Tums and I just take down the whole bottle. What do you think? An antacid, what's it going to do? It's going to remove acid. Okay, it's the opposite. So it's going to make this number lower. All right, here's my teeter-totter. And I take my antacids and it removes this, takes out the hydrogen ions. So this side actually gets lighter now. And in turn, if this side gets lighter, this side's turning heavier. So now my teeter-totter is in this direction. Okay, I've removed. So how do I get the equilibrium back? What if I have large amounts of this bicarbonate and large amounts of carbonic acid? If I start removing this, basically the equation is going to be go more rapidly in this direction to bring me back to equilibrium, right? I want to take this, I want to remove it, and I want to bring that teeter-totter back. Okay, so what if this carbonic acid ionizes and creates bicarbonate, and that would increase the amount of ions, and therefore if I draw this equation, I'm losing from this side and gaining to this side with the hydrogen ions. I'm bringing my equilibrium to the equation back. And now I'm also, when I do that, I'm also increasing the amount of protons. I lost protons and I want to replenish them because I want to keep that pH in that homeostatic range. Okay, so this is our first line of defense. These buffers are our first line of defense for keeping that pH within that homeostatic range. So this is a little
if you can work through this, you can help understand blood pH. We're going to see later in the semester when we start getting renal and respiratory systems, those two systems also have a way to help regulate pH. But our first line of defense is we have lots of bicarbonate in the blood and a good amount of carbonic acid, and the change in this drives my equation either this way, right? If this amount comes high, my equation is going to be pushed in this direction to remove these, and if this number gets low, the amount of hydrogen ions gets low, my equation is the rate of reaction goes faster in this direction to help replenish those protons. Okay, so that is how our buffer system operates. Alright, so through a lot of the reactions, let's start looking at those organic molecules or those biomolecules. Remember, we had 4 major ones. We had carbohydrates, we got lipids, we got proteins, and nucleic acid. Remember, these organic molecules, they're made with carbon, they're covalently bonded, and they're usually more complex because we're dealing with carbon. We can make all these different setups. Okay, you can see carbons, we can make these diverse molecules by using carbon kind of as our backbone to these molecules. Just remember, carbon can make 4 bonds, and therefore we can get more diverse molecules. So let's diversity of bonding, make long chains of molecules. We can make ring configurations, all right, and we can also do aromatic rings. That means we got these double bonds here. Okay, you can see all of these molecules they're basically made of carbon and hydrogen. We have the same amount of carbons, but the configuration of the bonds is what gives it its characteristic. Hexane, not the same as cyclohexane. They have different characteristics because even though they have the same amount of carbons and they're only bonded to hydrogen, the way they're bonded gives the characteristic of the molecule. Okay. So keep that in mind. We can change one little bond and it changes the characteristic. It changes, and many times, like a lot of these molecules, they're nutrient molecules. If we change some bonds, our liver doesn't have a way to process certain molecules bonded a certain way rather than molecules bonded another way. So like glucose compared to fructose, your liver has a hard time with dealing with fructose compared to, say, glucose. Even though they have the same, we'll see here in a second, have the same chemical makeup, same amount of carbon, same amount of hydrogen, same amount of oxygens, but changing one bond makes a big difference for our chemistry in our body. Okay, so keep that in mind as we go through these biomolecules. Small changes in the molecule can have dire consequences come chemistry-wise when it comes to our bodies. Okay. So diversity of bonds, again, carbon and hydrogen molecules make the backbone, okay, and they can be bound to what we call more reactive groups, functional groups. Functional groups have to do with certain types of bonds that we would find in molecules. A functional group, if you have a molecule, right, we have the carbon backbone making it a biomolecule, but if you have in middle, you have a carbon double bonded to oxygen, that is a carbonyl functional group. A hydroxyl, OH, found in there. Many of you guys find this highly fun because that is what makes a molecule an alcohol. Okay, when you go out Friday night, Saturday night, now that we can start going out again, right? We were locked down forever. I guess could have been doing this at home, but when you're drinking alcohol, it's the molecule you're drinking. An alcohol molecule has a hydroxyl group to it. Sulfur we won't see as much, but sulfur and hydrogen down there. Amino group, NH2. Hopefully that looks familiar. Amino, what molecule do you think we'll be dealing with that has an amino group to it, functional group? Yeah, amino acid. Okay, we're going to see amino acid. All amino acids have an amino group to it, functional group. Carboxyl acid, see, double bonded here, another O there. Okay, that carboxyl usually contains our organic acid, that carbonic acid that we talked about. That H2CO3 has our carboxyl reactive group, making it an organic acid. Just going back to that molecule we'll be talking about a lot, the amino acids, we will see what they have. Two functional groups here. They have an amino, all amino acids have an amino group, and they also have a carboxyl group because carboxyls will make the molecule a organic acid. And then a phosphate group, H2PO4. Hopefully this might look familiar to some of you. Where might we see the phosphate group? ATP, right? Adenosine triphosphate has 3 of these functional groups to it. Diphosphate would have 2. Monophosphate would have just 1 of these. Okay, so these are the functional groups. The ones we will be seeing most through the semester will be these 3. We'll see these a little bit, not so much the sulfohydro group, but these 3 here will be seen quite readily, and we'll be dealing with this one quite a bit through this semester. Because we'll be talking about what's called phosphorylation of a molecule or dephosphorylation of a molecule, and essentially that means phosphorylating means you're adding a phosphate group. Many of your proteins we'll be talking about are enzymes. They're regulated by either adding or taking away a phosphate group to one of the atoms in that molecule. So here's groups. Remember, this is a carboxyl. Helps make our organic acids. H2CO3, our carbonic acid. You see 2 O's, so there's another O in the carbonic, but we have a carboxyl group in this carbonic acid. Double bond ketones, those that are on anybody doing a low carbohydrate, a ketogenic diet, what you're creating is you're creating some molecules that are ketones. Your ketones that you create when you do a ketogenic diet have this reactive group to it. Aldehydes have a carbonyl, and then alcohols, as I said, have this. It makes these different classes of molecules we'll find in the body. We're going to be dealing mainly with organic acid and a little bit of ketones through the semester. And then, right, what's the other group? Amino acids. Amino acids have this along with that amino group, that NH2. Okay, so Organic acids, I want to focus on this because we'll be spending a good amount of time with that carbonic acid. Here is our lactic acid. When you're working out very strenuously, your body starts making lactic acid. We'll see why when we get to cellular respiration, why lactic acid is being made. But what happens as the levels of this get high in the blood, which way is my equation? Pushed in this direction. Okay, and what happens is that lactic acid ionizes and creates protons. What's an acid? An acid can release these. So as I make more lactic acid, I'm essentially releasing more protons, and my bud's becoming more acidic. My pH is starting to drop because I'm increasing the amount of protons. But luckily, right, we have that buffer system to help buffer out these protons in the blood. Okay, but as you can see, this isn't lactic acid is an organic acid because it has that carboxyl functional group. Okay, releases this proton. But these organic acids are weak acids because not all of this turns into this and releases a proton. Much of it stays as lactic acid also. Okay, remember, get this down, this law of mass action. Okay, make sure you understand that concept because we will be running through it back and forth throughout the semester. So if you get it down now, you don't have to constantly keep relearning it throughout the semester. Okay, so this ends part 1. I separate these up so when you go to download the videos or go to watch them, they don't take forever. I know this is a little bit longer, but I try to spend more time here because I know this is where these are the concepts you guys have to get, so you don't have to keep relearning them throughout the semester. Okay, so this is part 1. We'll jump into part 2, and then we'll be done with chemistry. But again, I can't stress it enough. I want you guys to understand these concepts because we will be using them throughout the semester. Okay, see you in part 2.